All right. Good morning, afternoon, or evening, OT699. Welcome to week 5. We are going to now move a little bit away from pure software, and now we're going to start dealing with the physical world through hardware, and specifically electronics. I'll get my screen share going now, and we can get right into things. So our main objectives for this particular week are twofold. So first, we're going to get into just a 30,000 foot overview of what hardware prototyping and actually creating real electronic devices that would go on the market, go out to consumers, what that would actually involve in terms of the procedure or the steps. Then after that, we'll actually get into how to do it yourself, at least that early stage where you create a working model. I'm going to get rid of my own video here and get right into prototyping. So just like with software, whether you're designing an app or a physical device, it doesn't matter. You have to start with the most basic idea, and that basic idea has to have value. The way that you figure out if an idea ultimately has value is by doing a lot of customer research. And even if you're not going to be selling a particular product, if you're going to be providing something to anyone, you need to really understand their life and what their particular issues are that you are trying to somehow make better. And it's almost the exact same concept as UI or UX for app design. It's the same exact procedure. The words are a little different. The jargon isn't necessarily a wireframe. And the early stage working model is actually called a proof of concept. Oftentimes you'll hear people call it a POC. That acronym seems to have different meanings depending on who you ask, so be a little careful in mixed company there. But proof of concept is almost universal in the hardware prototyping universe, as this is the first working model that you're going to be able to show somebody and say, do you like this particular thing? Do you think you could use it? And it's basically put together from parts that you can get on Amazon. I mean, it used to be only people with certain degrees or certain expertise that would be able to come up with an electronic device out of spare parts that could respond to the physical world, and if some sensor reads some value, do this thing, run this motor, make a light blink. That used to be something that was a real specialist kind of occupation, and now it's basically for anybody. They come in kits. Those kits come with tutorials. Those tutorials are meant for people who don't have extensive backgrounds or degrees in any particular area. So it's a really good time to be getting into electronics. A lot of the parts are very cheap. Individual lights and buzzers and motors are just a few dollars each, and even the real core of what we're going to be working with, the microcontrollers, the little mini computers, we're talking about $15, $20. We're not talking about hundreds of dollars. And there's really two choices when you get into this sort of field. One is an Arduino, which is what we're going to be working with, and the other is something like a Raspberry Pi. An Arduino is a microcontroller, so it's not a full computer. It requires that you plug the thing into a computer, and from your actual computer you can program the Arduino. And once you've given the Arduino a program to run, then you can disconnect from the computer and the Arduino will run that little program over and over as long as it has power. But you're not plugging a monitor into the Arduino and a keyboard. It's not something that has an operating system. You're not programming directly on it. You're giving it a program and it burns into the Arduino and then it runs it. And these programs aren't particularly complicated. Usually it has to do with sensing a couple of channels worth of data. Maybe it would be temperature, maybe it would be some kind of the light level in a room, or a dial that's being rotated. Some kind of physical change is now being put into the Arduino, and then the Arduino is going to have a series of if-then statements that it holds on to. And if the temperature is above a certain level, then it will have outputs, and those outputs could be lights, they could be buzzers, they could be motors, and in some cases you could even have it send you email if you download some add-ons and libraries. But for the most part, we're talking about physical inputs and physical outputs, maybe writing data back to the computer. If you have something more like a Raspberry Pi, now that is the situation where you have a computer that you're going to plug a monitor and a keyboard into. And to talk to that Raspberry Pi, you're going to just use something like Python, because the Raspberry Pi has an operating system and you can download and use Python on it. So it's basically just a tiny computer, and they look kind of similar when you see them side by side. The one on the left here, the green one, is the Raspberry Pi. The one on the right is an Arduino. There's a big difference in power between the two. However, starting with a Raspberry Pi is a little bit much. It's a little bit more complicated. There's more of a learning curve, and it's probably better to start by using an Arduino, and then if you need more, then go to something like a Raspberry Pi. And everything that you learn while using Arduinos is going to be directly convertible too. That you communicate with these in a very similar way. It's just a matter of which particular programming language you use. And of course, you can upgrade both in all kinds of ways. These are the base models that we're working with, but you can get add-ons that are almost as big as the actual Arduino or Raspberry Pi that let you talk to the internet, that let you do all kinds of complicated things. So this is just a beginning today. Now, if you wanted to make an electronic device, a toy or something, and you wanted to go all the way to commercialization, once you've built a working proof of concept, there's a few more steps. The first is to create a schematic, and that's going to be the formal standardized circuit drawing that electrical engineers use. These aren't really physical wiring diagrams, they're more formalized. Every component has a special symbol. It's something that people can read and figure out where the current is going in your circuit, do all of their safety testing, figure out exactly the right pieces, parts. It's not something that you would necessarily do yourself. It's something that you would probably get a specialist to help you with. The next step would be to convert that schematic to printed circuit board layout, and a printed circuit board is now the actual physical wiring. Instead of wires, they kind of melt metal onto a little chip, but in any case, this is going to be the actual working base of whatever it is that you make. What you think of as a computer chip is essentially a printed circuit board. And then the next part is to put your components onto that board. So if you have bells and whistles and motors and stuff, those need to be plugged into that flat chip that has wires on it. And you can oftentimes have the company that prints the circuit board also stick the electronic components on it as well. But this is, again, something that you usually outsource. Doing it yourself, you can make a few, but not much more than that. Once you get something back from the company, what it's going to look like is almost something like an Arduino. It just doesn't have any of the parts that you don't use. It's just the parts for your circuit. And then you would program it the same way you would an Arduino, plug it into USB, download your program, things like that. And the last step is to create some sort of an enclosure. You can't really have bare electronics in most consumer products. People get a little bit squeamish about touching things that have, pins and open leads and things and connected to batteries. It's a bad idea, and it's not good for relatively delicate chips either to be just open and exposed. So you need to create some sort of a plastic or metal house, and this can be 3D printed if you want a lot of them and you want them out of special high impact resistant plastics. You might go with injection molding, and this kind of customization is, again, something that you would have to send the plans out to a factory to do for you. It's not something necessarily you would do yourself, but 3D printers have become much more accessible lately, so this is probably going to be your best bet. And then you just kind of repeat this process until there's profit, because once you've made something that's almost in its final form, you have to go right back to your end user and see if the final product really meets their needs and if they like using it. And usually you'll have to iterate many, many times. Now, if you just want to make this thing for personal use, it's a kind of a different story. You don't need to go to factories and produce schematics or any of that, but what you usually do have to do is clean up the wiring. What we're going to be doing today involves sticking push pins into a plastic board, it's meant to be temporary. So at some point you need to actually connect the wires to the various electric components. And the way you usually do that is by melting some metal in between a wire and a lead to permanently connect them together. That's called soldering. And then that exposed blob of dried metal that you create has to be covered somehow, so you just wrap it with electrical tape or maybe heat shrink, which is this kind of rubbery tube that you put over a wire, and then with a heat gun, which looks kind of like a hair dryer, you just blow on it with some hot air and it shrinks and tightens and it creates a nice strong connection. The next step is some sort of case or holder, but again, you know, if you don't really need to go to a factory, a cardboard box could work perfectly well, and things like hot glue are amazing for just making one or two things that work and that hold together fairly well. So this is probably what is more realistic for most of us. And so for the rest of this particular lecture, we're going into just the initial proof of concept and describing how to make a working electric toy, essentially. And to do that, we're going to be using the Arduinos, the microcontrollers, rather than small computers. It's a lot easier that way. You don't need another monitor, another keyboard, and we don't need to necessarily learn a much more complicated programming language just to do it. Now, these come in all kinds of shapes and sizes. The kit that I recommended is an Arduino Mega, and that's one of the larger models. I think it's better because these things can get really, really small and really delicate. And starting your journey into electronics with highly breakable, fiddly things is just a bad idea in general. So I got the largest one I could find, and one that can really do the most in terms of different things, the most at once. So you can really do almost anything that you see in a tutorial online with a Mega. But of course, they've got other ones that are very thin, very small. There's some that are meant to be sewn into fabrics, so they're flexible. There's a whole world out there for these things. And of course, you don't have to look just for the company name Arduino. Arduino is producing essentially the schematics, and other companies are printing these boards. So you have an Elegoo. It's the exact same thing you'd get from the Arduino company. It's just printed in a different factory, and Arduino is totally okay with that. It is probably the reason why they're begging for donations when you download their software, but in general, Arduino seems to have the business model down pretty well. So a couple basics of electronics before we get into things, and some of this will be a review, I know, but it bears repeating just to refresh people who haven't been looking into this for a while. So first, we're going to create circuits, and by circuit, I mean creating a path for electricity to flow around a bunch of electrical components that do things, lights and motors and things like that. And we're going to be using direct current. Arduinos are all DC. Things like batteries and USB drives are all DC. And you can conceptualize what's going on in direct current circuits like a flow of water around, say, a faucet going to a drain, and the positive side of a battery is going to be the source. Wherever you see that +5 volts anywhere, or the positive side of a battery, you can consider that the source, like the water faucet. And then your circuit, and going through all the wires, is going to be the path eventually to the negative side, or the ground. And that's kind of important, that there's this convention that you go from the plus side to the minus side. It's actually a little contradictory if you look into the physics of how a battery actually works, but for now we cannot worry about that. Just remember, things go from the positive side to the ground. And that's different from alternating current, of course, what you get when you plug something into a wall outlet. The positive and negative side of a wall outlet changes every, it's every 50 hertz if you're in Europe, and 60 hertz if you're in the US. But in any case, it's constantly shifting which side is the positive side and which side is the negative side. And we're not using that kind of power today. What we're going to be using is the direct current, and because of that, it matters whether the flow is going in the positive or negative side of certain components. So in the kit that you have, there's an active buzzer and an LED. Both of those are polarized. You have to make the positive side of a circuit hit the longer of the two little legs that those components have, the little leads. They're labeled on the buzzer, they're not labeled on the LED. You just have to know that the positive side of a circuit has to be the longer lead. The current will flow into that side, through the component, and out the negative side, eventually going to the ground. It has to be that way because if you try to send electricity through these components in the wrong direction, it can either not work or harm the components. You can burn them out, you can hurt your circuit or the Arduino. So you have to be a little careful about the direction of current flow. And a little bit more about the kit that you got. There's a lot of different components in there. Here's a few of them, not necessarily an exhaustive list here, but the star of the show, of course, is this Arduino here in the bottom, and I'll make a little laser pointer here. So this component here is the Arduino itself. The thing over here, the power supply, that we'll get into in a few minutes. That is not actually necessary. It's just a nice to have. It helps you to prototype a few test circuits without involving the Arduino at all. It basically gives power to the breadboard, which we'll get into in the next slide. Of course, we've got a battery if you want to power this thing without the computer, a bunch of wires, some lights, LEDs specifically, light emitting diodes. There are two forms of buzzer. The one that I was showing before that has the two different sized legs because you need to send the current in one side and out the other. That's an active buzzer. That means that you just have to hook this thing up to a battery and it will buzz. The passive buzzer is a little bit different. If you just go from having no current flow through it to, say, connecting a battery, it will just make a click once. And so to make this into a buzzer, you need to send pulses of electricity through. So on, off, it'll go click, 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 click really fast. And eventually, if you can make it click fast enough, it will sound like a buzz. So there's kind of a difference. This one will just buzz if you give it a solid current. This one you have to send a special pulsed signal to. We're probably going to use just the active buzzer today. There's also a couple of different kinds of switches. This tilt switch we'll get into. It's a really neat component. Basically, it turns a circuit on and off depending on the orientation of this thing and if you're moving it or not. There's a photoresistor that's going to control the flow of current around a circuit depending on how much light there is showing on that particular panel up at the top there. And of course there's push buttons, and the push buttons that came with the kit are really small fiddly things. They're just, I'm not going to use them for anything because they're really not worth it. You can buy a really good big push button for 50 cents. It's just, they really skimped out on the push buttons. I mean, we're going to use mainly the tilt switch because it's a little bit easier to work with. So now before we begin actually building circuits, it's probably good to show you some of the pieces that you just saw blown up on the big screen in real life, because they are a little bit smaller than you might expect. So let's start with the LED, the light. It's a little tiny component that looks like this. And if I can get the light going right, you can see that there's two metal legs sticking off of this plastic green light here, and one of those two legs is a little bit longer than the other. Keep in mind that this is one of the components that you do need to keep track of which is the long leg and which is the short leg, because the long leg has to ultimately connect to the positive side of the battery or the plus 5 volt side of the Arduino. It has to be connected to the positive side of the circuit. And I'll make that more clear as we go. The little legs themselves are very thin and bendable. And in order to plug things like this LED into your breadboard, you just press them in so that they stick like that. In the diagrams that I'll be providing you, you'll see that sometimes you need to bend the legs of a component like the LED a little bit so that they will be about 3 holes apart. And that's so that we can keep everything a little bit more clear in terms of diagramming out the circuits that we're building. And that's totally fine. It's totally normal and expected to bend the legs of these kinds of components. You just have to be a little careful about it and make sure that after you're done sticking this thing into the board, that the metal legs don't touch each other. That's probably not going to be an issue for an LED, but there's also a little component called a photoresistor that we'll look at, and that is something that looks like this in real life. It's just a very small, flat little button on top of 2 legs. And it has these really long, wiry-like legs coming out of it. And when you're pressing this particular piece into this little board, you want to make sure that you grasp the legs very close to the bottom so that you don't bend the legs too much. If you just grab it way at the top and try to press it in, it won't work. It'll kind of bend, and you want to make sure that they don't cross like this and touch each other. So this is going to be one of the more fiddly pieces that you have to be a little careful with. A couple other pieces that we'll be working with. One is a buzzer. The one we'll be working with today has a white sticker on top with a plus sign on one side. That's because this buzzer, just like the LEDs, has a positive side and a negative side, just like a battery. And the positive side, again, is going to have the longer leg. There are 2 little legs sticking off of here, and the longer leg is going to be the one that you put on the positive side of a circuit. You won't have to necessarily know what the positive and negative side of a circuit is in this tutorial, because I'm telling you exactly where to put each leg in this breadboard. The breadboard is itself labeled, where every hole has a row label and a column label. They go from 1 to 60 along the columns, and from A to J going up along the rows. Orient this breadboard the same way on your desk as in the PowerPoint presentation, with the numbers going 1 to 60 left to right, and the letters going A to J going from bottom to top. That will help make sure that you're not putting together a circuit upside down from the way you're looking at it on the screen. There are a couple other components as well. One is a tilt switch, just this little tall metal cylinder with 2 legs sticking out of it. And this one, because it's a switch that you need to move around, we need to not just plug it into the board and let it sit there. We need to extend the legs a little bit. And that's going to be something that we do with a couple jumper wires. Jumper wires come in 2 varieties in your kit. One is going to be these ones that have pins on each end. Those are male-to-male jumper wires. But there's also some ones that have a pin on one end and a little rectangular plastic plug on the other side. So these are going to be the male-to-female jumper wires. These ones were connected together with a little bit of plastic so that they all kind of came in a ribbon or a band. Now that's just how they come. To take off 1 or 2, you just peel them apart. That's totally normal and expected that you do that. Finally, there are going to be 2 sensors we'll use next week. We're not going to get into them this week, but I should just show you them anyways. One is a distance sensor. So that's this big piece that looks like that. That wasn't inside the Elegoo kit. This is something separate that we asked people to purchase. And one piece that was in your kit was this little black plastic dial with 3 pins sticking off of the base. It's just a little dial that you twist like that. It will probably have come apart in your kit into 2 pieces. The bottom will be this kind of flat looking cylinder with the little pieces hanging, the little feet hanging out, and it says in white letters 10K on it. The little dial-y part fits right back in to the base, shouldn't take any pressure. It's just a real easy fit. And then you can use this component. So if it comes in two pieces, don't worry, that's normal. It didn't break. It's supposed to be able to come out like that. This is also going to be a piece that we're going to need to attach the male to female jumper wires onto the legs of, so that we can hold the dial like this in one hand and move this around a little bit without it being directly onto the circuit. You can plug this into the breadboard and have it be fixed, kind of like this. However, the orientation of the clips inside those holes isn't quite right for this, and I was trying to do it earlier and one of the legs bent a little bit too much, so I thought it's probably going to be better if we just extend the cables out a little bit, extend the pins with cables, but that'll be more next week. We also are going to start with just using that breadboard to make some circuits and powering the breadboard with a battery. You did get a 9-volt square battery in your kit, as well as this little adapter. You just plug the adapter onto the top, and now you can plug the 9-volt battery into either this power module. This thing should turn on and off when you press the white button. It basically goes onto your breadboard like that and allows you to build little circuits on your breadboard and then turn them on and off like with the white button. You can also power the actual Arduino with this as well, like that. See? Or more likely, you'll power your Arduino with the USB plug. This will go into the silvery metal part, and then the Arduino board will get both power from your computer through this USB cable, and it will establish communication with your computer too. That'll come in handy next week more than this week. I think that about covers the pieces that we're going to be using, at least the real life tour of them. So now we can get into actually building some things on that breadboard, buzzers, things that light up. And that will be where we get into the real fun part. But remember, you should keep the PowerPoint presentation open off to the side while you're viewing the rest of this recording, because it's going to be a lot easier to see where everything plugs into that board on the big PowerPoint slide that has all of the holes labeled and where everything should go, rather than relying on kind of squinting at the video that I show of my actual setup, where the camera won't quite focus enough to read the numbers off of the breadboard, but I'm using the camera to show you what the built circuit looks like and that it, something lights up and buzzes when you do something. For the actual building of the circuit, you're probably going to want to use the PowerPoint presentation, and that will make things a lot easier. And of course, if you have any questions, let me know. The most common things that people do wrong are putting the long or short end in the wrong holes, like flipping the whole component, or just generally misaligning things. They were aiming for column number 20 and hit column number 21 instead. Those are the most common sources of errors on building circuits like this for the first time, so be aware of that. So moving on, this thing here is a breadboard. I don't know why it's called a breadboard. I've never seen bread put on a breadboard, but that's what they're called. These have been a mainstay in circuit prototyping since forever, and they all follow a specific set of rules, basically. So first, on the two sides, you'll see there's these long lines, one red and positive, the other blue and negative. What that means is that all of the little holes that you can push wires and pins into, all of the holes in this row, underlined by the red line, are all connected with each other. It's like one wire underneath. So it doesn't matter if you plug something in here or if you plug something in there, they're all connected to each other. And the same is true for the negative side. Usually what that's used for is that you have something like a battery, and the positive side will be plugged into one of these holes, and the negative side would be plugged into one of these holes. And then anytime, anywhere along this breadboard, you have a component that needs to get either the positive or the negative side of the battery, you can just plug into any of the two holes along that rail. The two sides look like mirror images because they are, so the whole bottom and the whole top are just mirror images to each other. They're not connected. It's basically like you have two halves that are just repeats of the same thing. If you want to have a component on this side that gets power from this side, you actually need to send a whole wire down. You can't, nothing is connected underneath between the two, the bottom and the top half here. And then you see all these little dots. Those follow some conventions as well. So for one, the columns are numbered from 1 to 60, or 60 something. And the rows have letters. So A through E on the bottom half and F through J on the top half. These are also connected to each other. Basically, in any given column, like say column 10, all of the little pinholes from A to E are connected underneath. It's one piece of metal under there. So if you wanted several components to be connected together, you could just plug them all into this one column. And again, they're not connected to the other side. So F through J is a totally different thing. All of the ones F, G, H, I, and J, 10, they're all connected to each other, but not connected to A through E. And the naming convention is going to be helpful for us today because it's a little hard to see where things are plugged in sometimes, especially if you have more than one component. So wherever possible, when I have some wiring, I'm going to say where the wires go. So it might be A10 to A15, for example. And the highlighted hole here is A10 for reference. So now we get to some of the fun stuff. The breadboard has this power module thing that you can attach to it. Basically, you plug the battery into the little adapter here. And what this component does is that when you press the on-off switch, it gives power to the two sides. So on the bottom half here, it's providing a 5-volt signal to this entire positive rail. And then the negative one is going to be ground. And it does the same on the other side, but there's a little piece that we're not going to mess with that you can take on and off that lets you choose either 5 volts or 3 volts as the power. And so they set it up just in the package as the bottom half is 5 volts and the top half is 3, and we're going to use the bottom half. Either way, what this lets you do is plug a bunch of things like lights and buzzers and things into the breadboard, test out your circuit by pushing the on and off button, and if you think everything is good, then you can actually make the Arduino control things and get rid of this power source altogether. So let's see how that works. What we're going to do now is make a buzzer buzz, a simple circuit, and use that as kind of an example. I'll give you a quick preview and then I'll actually make it so you can see what it looks like in real life. So we're going to get the power source stuck onto the breadboard, and then a couple of jumper wires are going to bring the positive current from this rail around the buzzer, which is marked by number 1, and all the way back to ground. So the flow is going to go from the positive end into column 20. And remember, all these holes are connected. So the next jumper wire is going to cross the river here. It go from E20 all the way to F20. And then all these are connected. And we're going to put the buzzer in the very last or the very top row from 20 to 23. And remember that the active buzzer has one long side and one short side, and the long side has to be the one facing the positive current flow. So since this wire here around column 20 is bringing the positive flow of current, we're going to put the long lead in J20. And then the short lead will automatically go into J23. You don't have to bend the leads on this particular component. So I'm going to see if I can get the second camera going and actually build this thing. Okay. Second camera. Okay, so here's what it looks like in real life. Just a little plastic breadboard. And this is the power module that came with your kit. It's not really auto-focusing, but that's okay. On the bottom, it has a couple of pins you can kind of see, 4 on each side. Those have to plug into holes in the breadboard. It doesn't matter exactly how far up or down you go. So just kind of put it over at the end, make sure each pin goes into a corresponding hole. Like that, it just kind of snaps in. Try to make it so it's not diagonal, like that. And then you've got the 9-volt battery. And that's going to just plug into the adapter, like that. Next thing is going to be the little buzzer. The sticker has a plus sign on it on one side. That's going to correspond with the longer of the 2 legs. It's a little hard to see. The camera's not focusing that well, but one of the metal legs is longer than the other. That metal leg is going to go into J20, and then the short leg is going to fall into J23, like that. Then the next thing that we're going to do is create the circuit to flow from this positive rail around the buzzer to the ground. So we'll start with taking this positive and going to row 20 to give it power. This is now A20. And I've got these listed out in the PowerPoint as well. So then we're going to cross that little bridge from E to F. Now the positive side of the battery has essentially contacted that one leg of the buzzer. And then from the other side of the buzzer, which is in column 23, we're going to do the exact same thing. Instead of just crossing the bridge and doing this separate stuff, I can now go from F23 all the way to ground, like that. And I think the camera's kind of got it. So once we're there, all you have to do is press that white push button and you'll get something like this. So that was annoying. But we just gave it a direct current, essentially connected the 2 ends of the battery to the buzzer, and it buzzed. So that's terrific. Now we're going to make it a little bit more complicated. Let me go back to the PowerPoint here. Okay, so this is the circuit we just did for reference. Now we're going to add a light. So just having a buzzer is cool, but having a light go on at the same time is even better. And so to just kind of guide you through what the current is actually doing, it's going from the positive rail up through the active buzzer. But then instead of this F23 jumper going straight down to ground, we're going to move it over to another column. It doesn't really matter which. I'm just picking 30 because it's a round number really. But then that particular current, which is still on the positive side here, is going to flow into the positive side of the LED, the long leg of the LED, and then through the LED and back all the way to ground. So this is what that will look like. Switching over. Okay, so I'm going to take this little jumper that was going to ground, and I'm going to move it over to another column, which is column 30. Then take the LED which has a long leg and a short leg. And I'm going to try to stick the long leg into G30, which is just above where I put the last jumper. And then G33 will be where the ground leg naturally falls. And be a little careful pushing these things in. You have to sometimes bend the leads a little bit to get them to actually get into the holes, and then you have to be careful pushing them in that you don't bend them further. Or there's quite a lot of delicate little parts here, but you still need to push them in enough so that they don't just fall out. And then finally, we're going to go from F33, which is just right underneath the ground leg of that LED, and jump all the way to the ground rail at the bottom, like that. So now, when we send current through this thing, we get an LED and a buzzer at the same time. Okay. So now we're going to make it even more complicated in one moment. So moving forward one slide. Now we're going to replace the buzzer with a photoresistor. So the photoresistor is going to go exactly in the place that the buzzer was. And let me just briefly explain what the photoresistor does. Anytime you have a circuit, you have various pieces, parts that resist the flow of electricity through the circuit. A buzzer is a pretty good resistor, it turns out. And I'll get into that a little bit later when we talk about how not to blow up electrical circuits. But in general, the idea is that each part that you put into the circuit will either allow a lot of electricity to go through, or it will resist it somewhat. And if you have a very resistive element in your circuit, no electricity will flow whatsoever. You can kind of think of two wires that are just near each other. They're not going to send lightning across the air to each other because air is pretty resistive. So if you have too much resistance in a circuit, nothing will happen. It turns out that a photoresistor has a resistance that depends on how much light there is showing on it. So in the case of this particular model, when there's light, it will allow current to go through it, and in the dark, it won't. So if we cover up the photoresistor, it should turn off the light. So let's see how that works in reality. And of course, to get this to work really well, you'd have to tune the exact amount of resistance in this to the type of LED you're using. This is just kind of a demonstration, so we'll see kind of a dimly lit LED turning on and off when we stick a hand over the photoresistor. Let me just get the other camera back on. All right, here we are again. This component here, the little buzzer, is coming out just for now. And I'm going to put in the photoresistor, which is not in focus, but trying. Well, you got the idea. One thing to note about this, the leads are really, really quite liquidy. Be very careful trying to push these in. You want to make sure that the two legs don't touch each other, and you want to make sure that you don't accidentally rip them off in the process of pushing them into the holes. Just be a little bit cautious or aware of that. It's not a very expensive component or anything, but it would still be sad to break it in half. Let's put those in the exact same holes that the legs of the buzzer were in. It doesn't matter which one goes in which hole because this particular component is just a resistor, so it doesn't matter. It will resist current flowing in either direction. So this is going to go from I guess it was 21 to 24 instead of 20 to 23. I think I just kind of missed the hole on that last one. Either way, you get the idea. Okay. So there's what it looks like. And if I give this circuit a little bit of battery power, you can see that the LED has lit up. And if I cover up that photo cell with the pencil, it goes out. All I'm doing is blocking the light, not making any physical contact with it. And it works better if I put my hand over it, but you can't see it as well, so there we go. Like that. All right. So now for the rest of this, we're going to take the photoresistor out and put the buzzer back in. Going back to the PowerPoint for a second. Just as a quick review, the circuit basically was the exact same one as before, but now it went through the photoresistor, and the photoresistor served as kind of a drawbridge, did not let anything pass through when there was no light. Okay, so now if we go back to the buzzer light combo, which is what we just did by putting the buzzer back in, there's an extra piece to all of this that so far has been neglected, and that's that we're using the push button on the power module to turn things on and off. And that's okay, but it's sort of cheating a little bit because we're not building that circuit or we're not building that switch. And also what we'd really like to do is play with some of the neater elements that came in the kit, one of which is the tilt switch. And the tilt switch as a diagram looks something like this inside. It's a hollow tube with a metal ball at the bottom. And when it's upright, gravity is pulling that ball down and it's connecting the two leads so current can flow through it. If you shake it or tilt it, that ball comes dislodged from the base. And when that happens, it creates a gap so that current can't flow through this switch anymore. So it's technically on when it's upright and off when it's tilted. And it's actually really sensitive. So even things like vibration or sudden movement will dislodge this little metal ball at the base. So it actually can be used as a movement sensor as well as a tilt sensor. It's not really an angle sensor. It's more just anything that has dislodged that ball. And that can be an interesting thing to play with. So let's see how that works. The circuit is going to be very similar to the one that we just built, but a couple of things have to change. So first one is that tilt switch, it has two legs that could be stuck directly into the breadboard, but then we can't really move it. So the best thing to do is to take two jumper wires and stick them onto the legs of this component. It doesn't matter which leg is which, they're both the same size. It doesn't have a direction of current flow or anything like that. And the kit came with some female to male jumper cables. So those are the ones you're going to want to use. And what we're going to do is just take the current that had flown out of the LED, and instead of bringing that all the way back to ground, now it's going to go in one end of that switch, through it, and then the other end of the switch will go to ground. So let's see how that works. Okay. So first, this is the tilt switch that came in the kit. I'm taking these jumpers that have the female on one side, male on the other, and plugging them in so that you can have something that actually moves around and isn't attached to the breadboard. This jumper that had gone all the way to ground from the negative side of the LED is now going to go off to another column. I don't remember exactly which it was in the PowerPoint diagram, but it doesn't really matter. I guess I'll make it E40. And then same column will have one of the two legs of the switch. So I'll stick that the next letter down, so that's now going to be D40. And I'll go over to column 45 for the other end. And then we need one more jumper to go from, in this case, C45 over to the ground. And it doesn't matter which ground pin because they're all the same on that rail. So now the idea is that the current will flow from the positive rail through the buzzer, through the LED, and through this switch. If the switch is closed, if the switch is open, the entire circuit will not get all the way to ground, and therefore nothing will happen. No buzzing, no lights, no nothing. So let's see how that works. So right now you can see there's the LED on and it's buzzing because the ball is sitting in the bottom of this component, and so it's making a connection. But if I tilt it, the ball has now moved towards the top of this component. It's not connecting the two leads anymore, so it's stopped. And even if you shake it a little, it'll work because the ball rolls around in that cylinder. Okay, so you get the idea. Back to the PowerPoint. Okay. So now is probably a good time to point out that I haven't been totally haphazardly putting things on the board without checking anything first, because you do have to be a little bit careful with delicate electronics. And before we move into using the actual Arduino to do some of these things, it's important to talk a little bit about general safety. And I don't mean anybody's going to be blowing anything up or melting anything with these circuits, but there are some things that are good or bad for the long-term health of your Arduino, and you can burn out fancy electronics if you do things wrong. So let me just go over a couple of basics. First, when we're talking about electrical circuits, the three major words that you need to always have in mind are current, voltage, and resistance. Electrical current is like what we were talking about before. It's like the flow of water through a hose. Voltage is going to be, in that analogy, like water pressure. So you've got the pressure and the flow. Resistance is anything that resists flow, and there's a relationship between all of these elements. Voltage is equal to current times resistance. That's not necessarily an equation you have to memorize. It is an extremely important one. It's called Ohm's law, and it's actually so popular they've come up with neat little mnemonics for people who don't want to remember the equation. Basically, in electronics, I is current, so you can put your thumb over the V or over the R and it will tell you how to get that particular element. So if I cover the R with my thumb, it says V over I, so voltage over current equals resistance. Or if I cover up the V, then current times resistance equals voltage. So it's kind of a neat little mnemonic that they use. The important part for you, though, is that this relationship implies a circuit with low resistance is one that can have high current. So high current is bad because it kills electronics. Think about what would happen if you took a 9-volt battery and you just, with a paper clip, connected the positive and negative side. There wouldn't be much resistance at all because it's just a metal wire. The battery will get hot and spark and can melt, things like that. It's usually pretty bad. You can start fires. So generally speaking, you don't want to have a very low resistance in a circuit. It's safer to have more resistance, because if you have too much resistance in a circuit, it just means the electricity doesn't flow through it. It's like somebody didn't flick the switch on yet. That's it. And so oftentimes in Arduino tutorials, you'll see resistors, which are these components with those stripes on them. You have about 100,000 that came in your kit. You'll see resistors added in various circuits. The purpose of those resistors is just to keep the current down so that you don't damage your fancy electronics. And these resistors also come in different flavors. They're labeled by how much they resist electricity. So higher numbers would be more resistive. And they go from, I think, one of the lower ones is 220 ohms is the unit of resistance, all the way up to, I think, 100 kilo ohms. And in general, you don't need to worry too much about calculating this stuff out, but you do need to have a couple of rules of thumb associated with resistance in general. The two that are most important, and I'm going to throw two more vocab words at you. If you add elements of a circuit that are resistive, so you add resistance in series, that means end to end. So the flow of electricity is going in one, out the other, into the next, out that one, like this diagram in the top right. If you add resistance in series, usually the circuit is going to be safe. If you have a circuit that you know works and you add stuff to it in series, you can't break anything. All you can do is slow down the flow of current in general so that stuff doesn't work, but you're not going to burn anything up that way. However, if you add resistance in parallel, meaning that you've got something like a 5-volt source splitting off and going into several components that all converge later and go to ground, that is a different story, because when you add resistance in that way, you actually can increase the current going through the circuit, and that's when you can wind up in trouble. So if you're playing around with new components and you're not really sure, generally try to avoid the situation of branching from one plus 5-volt source out into lots of different elements and then having them all come back together again, unless you have some idea that this is going to be safe. Now, there are formula for actually calculating out what the total resistance in a circuit will be, as well as the current going through each component. But for a hobbyist, that doesn't really matter so much. You can buy a $5 multimeter like this one here, and it will tell you how much resistance goes from any point to any point within a circuit. So if you're in any kind of doubt about whether or not you've got too much current or voltage, or anything in a circuit that you might want to measure, you can measure it very easily and very cheaply. So if you get into electronics, you might want to purchase a multimeter. It's also good because sometimes resistors, if you use them a lot, you can break their leads, but you can kind of feel them. They're very, very finicky little wires, and if you push them in and out of the breadboard enough times, they can start to break. So if you've got a resistor and you're not 100% sure if it is actually a 220 ohm resistor or if it's broken and doesn't do anything, you can use one of these multimeters to verify the resistance. So you don't need to read the label. If you've lost the label, you don't need to read the stripes on the component which tell you the resistance. You can just measure it directly. Anyways, that was just a side tangent, but important before we get into fancy computerized electronics. So what we did was one of the most basic things you can do, turn a light on and off with a switch. But what if you wanted to have the light blink at a variable rate? Or what if you wanted to turn the light on when the switch was in its off tilted position? And what if you wanted to make the light blink faster when the tilt switch was tilted and slower when it was upright? Things like that, right? Or maybe you want to use a sensor, and depending on the sensor reading, like the temperature in the room, turn on a circuit. This kind of thing isn't so easy to do with just a battery and a breadboard. You kind of need a computer sitting there making some if-then statements, and that is what a microcontroller like an Arduino is for. Let's do a quick tour of the Arduino. This is the microcontroller, the brains of the operation. I'll make a laser pointer here. This is really the whole thing. Everything else is sort of peripheral to this in some way. This is where the computer program is stored and where everything is run from. On the bottom side, you see a lot of little pins that you can push things into. Those are your analog inputs. So if you have a sensor, it will sense something and turn it into voltage. In this case, these analog inputs read between 0 and 5 volts. And of course, because these are circuits that we have to build, there's ground and power sources, both 3 and 5 volts. The other side, and in fact along the bottom as well, are digital input outputs. So digital input/output just means that these pins either become plus 5 volt sources or they become ground. It's yes or no, 1 or 0, high or low. You can't send out a 2 3/4 volt signal through these things. All you can do is set them to high or set them to low. And if they're high, then they basically become the positive side of a battery, and if they're low, they become the negative side of a battery. The ones on top here, as opposed to the ones on the bottom, the ones on top have this special acronym, PWM. That's not really a property of the digital input-output itself. It's more that the software allows you to communicate with those particular pins in a special way. Basically, it says, make a pulse train, so on, off, really, really fast, and you can control the proportion of time on versus off, and that's good for a variety of things. One of them being dimming LEDs. Another is that you can sort of fake a real analog output. In some cases, you might want to have, say, a signal that goes from 5 volts to 3 volts to 2 volts. You can't really do that, but if you have this pulse train going through, there's ways you can process that information later and kind of reconstruct what looks like a regular analog output. In any case, we're going to use them just in their typical form of on versus off, making it either a 5 volt source or a ground, and that's it. There's also a built-in LED that we'll be using. Over on the side, there's the USB connector. This provides power to the board and communication with your computer. The computer can use this serial cable, this USB cable, to upload a program to the microcontroller, and the microcontroller actually has the ability to send data back through the USB cable to your computer. It's also got the ability to take that 9 volt battery that we were using before as its power source, so you don't need to connect to a computer at all. And in fact, that brings me to the next slide with a couple of different configurations. One configuration that you can work with is to have the Arduino plugged through the USB cable into your computer, and then the Arduino itself is going to send wires out to the breadboard to make your circuit elements move. Another option is to just discard the computer entirely, power the thing by battery, and you can do that through the 9 volt adapter. And then a final configuration, which it's kind of useless for what we're doing really, is to keep what we had. So the 9 volt power source is now powering the breadboard through this power module thing. But then the power module has this USB plug. That's sending the 9 volt power over to the Arduino itself. So basically it kind of gives you a combination of these other two. But we won't really use that one. This might be more important for if you had motors, and we'll get into that in a little bit. All right. Now for the fun part, we're going to actually download the software associated with the Arduino, plug the Arduino in, and actually start using it. First, to get things started, I've uploaded the contents of the mini CD that came in your kits, because nobody has tiny optical drives anymore anyways, so that was kind of weird of them to do that. But in any case, that folder that was on that CD came with a variety of PDFs. One of them was called Basic Starter Kit for Mega, blah, blah, blah. And that gives you instructions for 20-something different projects that you can do with your Arduino. And it also has a full set of installation instructions. We're going to skip that part. I'm just going to download the Arduino software myself and show you what I'm doing along the way. I have Windows, so I'll be showing you the Windows version of this, but for Macs it's going to be very similar. You go to the Arduino website, to the download site, download the zip file that says for Macs, unzip the zip file, and drag the Arduino icon into Applications folder, and it should just work. Occasionally, if you have an older Mac, you may need a set of other instructions. both the PDF that's provided by Elegoo and this other website that I've put on this page here talks about some of the solutions to problems if your Mac doesn't work. Most likely, if it's a fairly modern, a fairly recent Mac, it should be totally fine. But of course, contact me if not. I'm going to go to the website now, though, and download the actual Arduino software. So here is where you download things. For Windows 7 and newer, you're going to click on the top one. The zip file you can also use, but if you do that wrong, sometimes you wind up with the drivers not being installed automatically. So I would prefer if everybody just clicked on the top Windows 7 and newer option. Don't download the app. It seems to be a mess and it doesn't quite work right, and it kind of messed up my computer for a minute. So click on the top one if you have Windows. If you have Mac, there's only one option. So I'm going to click on the Windows 7 and newer. It's going to beg me for donations because they're letting everyone else print their boards. I'm just going to say download. It says, do you want to save the .exe? Yes. And when I've got that, I'm going to run the exe. Do I want to make this blah, 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 blah? Yes. Do I agree to the terms and conditions and sign my life away? Yes. Install everything, including the USB drivers? Yes. Put it in the same folder that everything is in program files? Yes. It's extracting everything. Installing software? Yes. Would you like to install this software? Yes. How about this software? Yes. Close. Okay. So now I can close this. And if I just go to my search and type in Arduino, I've got an Arduino app. And I'll show you what it looks like. So first thing that came up, of course, is this Windows thing. That's totally fine, allow access. And what popped up for Arduino's IDE is essentially a blank scripting page. They call their programs sketches, and this is just the blank page that you get. There's nothing else. It just pops up like, so you want to start a program? Go. That's all. It filled out this for me. We'll get into that in 1 minute. But first, the main question that would be good to ask is if it actually installed correctly and can now communicate with your Arduino. So what you're going to do is plug the Arduino in through USB to your computer. So I just plugged it in. And go to Sketch, Tools, and go to Board where it says Arduino Uno. We have the Mega, so go over to where it says Arduino Mega, like that. And under Tools also, one thing to notice is that the port has been detected that I have this thing plugged into COM3. Your port would probably be different. But either way, it has now connected to my specific board, the Mega, and it detected that I plugged it into the USB. Okay, so the first thing that you're going to do to test out that this really works is find an example script. And under File, you can go to Examples, to Basics, and then to Blink, and open that sketch up. It looks like this. What this particular thing does is blinks an LED on and off. What it does that's kind of nice is that it blinks its onboard LED. So we don't even need to make a circuit. We can test if this thing is working just by going up to the very top where there's that little right-facing arrow to upload and press that button. It says it's compiling the sketch. It's sending that over to my Arduino right now. And it said the serial port was not detected. Retry upload to the serial port. Okay. Now it worked. I don't know why it said that, but now it's cool. So if that happens to you, don't worry. Just click OK. And I can prove that it's working because this particular program says to turn an LED on for 1 second and then turn it off for 1 second. So we can see if that's actually happening with camera over here. So here's what's now happening to my Arduino. That is the onboard LED, and it's being told turn on for 1 second, then turn off for 1 second. And at this point, I don't need to be connected to the computer anymore. It will still keep doing that as long as there's power. So everything is now working totally fine, and we can actually start to mess with this code a little bit. First, I want to point out one or two basics of what a sketch is. So I'm going to stop this and go back to the other view. All right. So this is that blink one, but I'll just show you the blink part first. And I've got this also in the PowerPoint presentation. This void setup right here, everything that you put before the curly brackets is going to tell the Arduino what you want to do with your pins, basically. So you can define a particular pin as an input that you're going to read from, or as an output that you're going to be writing to. You've also got some space between the two blocks that you can define variables that might be useful later on. This is the stuff that's going to run one time only. And then from that point on, what happens is the Arduino will enter this void loop. I don't know why they call it void necessarily, but this is basically just a loop that keeps going over and over again as fast as the Arduino can forever. And everything that you put in here will be repeated over and over and over and over again, unless you find some way to break the Arduino out of that. So once you run one of these things, it's going to set this in motion, and it's not going to stop until you cut power. So just keep that in mind. Let's see what the blink program was doing. The blink program in the void setup said, I would like LED built-in pin to be an output. It happens that LED built-in is just pin 13. So we could actually replace LED built-in, that word, with the number 13, and it would still work totally fine. Pin 13 is an actual pin that can go out to a breadboard and power some circuit element. It just so happens that it's linked to the internal LED on the Arduino itself for testing purposes, so that's convenient. Once we enter the void loop, it does two things. First is it writes the pin 13 to be high, meaning turn it on. That will turn the LED on. And then it says delay 1000. So now it basically tells the Arduino to go to sleep and do nothing for 1000 milliseconds. And then when it wakes up, it does the next line. It's going to write the pin to low, so it turns the LED off. And then it waits and goes to sleep for another 1000 milliseconds. And then it starts back up at the top of the void loop, turns the thing on, waits a second, turns the thing off, waits a second, loops back up to the top, and repeats forever. So that's what's happening. Now, if you want to make this a little bit more interesting, you can play with the timing of that blink just to see how that looks. So for example, let's say I make the LED turn on only for 100 milliseconds and then I turn it off for 200 milliseconds, something like that. If I upload this, I'll switch over cameras before changing it so you can see the difference. Okay, so here's my slow blinking light. Now I'm just going to press the green right-facing arrow that says upload. Okay, now it started blinking much faster. Okay, now we're going to make life a little bit more interesting. I have this next couple of steps in the PowerPoint, but since I'm on this camera now, I'll just show you. I'm going to take the breadboard that we just had. This is the exact same setup as before with the tilt switch and all. Let me get it so you can see it. All I did was take the power module off. So this element here, I just took that off. Everything else is exactly as it was last we viewed the breadboard. Now, there's just one or two small changes that you can make so that instead of powering this little onboard LED, it's going to power this entire circuit. Previously, on the positive rail, I had this jumper. I'm going to take that out. And instead of going to the positive rail of the breadboard, I'm going to put it into pin 13 on the Arduino. It's a little hard to see, but these are much easier to see in person. The little push pin just went into the number 13 right here. And then the next thing I'm going to do is ground the Arduino to the ground of the breadboard with another jumper. So I take the ground, which is right next to pin 13, and put it in the blue negative column, like that. Hang on. Just fiddling with it, and so it'll stay in. And remember how we had it on a switch? Still works. So now you've got something like a motion detector circuit with a buzzer and a light. All right, we're going to make one more modification before we can call it quits for today with new circuit designs. But this one's a really important one. So we're going to make the switch that we were just using a digital switch. So that means that instead of the circuit itself being broken or connected when the tilt switch is on or off, tilted or untilted, what we're instead going to do is make one of the digital pins read the state of that tilt switch, and then in the program itself, we'll decide what to do with that information. That means that the switch can be on or off, and it doesn't actually change anything about the buzzer and LED circuit. It's completely disconnected. It's a different thing altogether, and that's nice because you might want to be able to do something like have the buzzer and light go off when the switch is tilted. Previously, we couldn't do that because tilting the switch disconnected the circuit. But now all we'd have to do is change one line of code somewhere, and now when the input pin reads that the switch is disconnected or tilted, then we would tell pin 13 to go make the buzzer and the light go crazy. That would be a kind of tilt or movement alarm. So let's see how that would look. Major changes here are just that I took the negative side of the LED and brought it all the way to the ground rail, and then took the switch, the tilt switch, and just put it over somewhere outside that nothing else was being used over here. So in this case, I put it in E40 and E43. It doesn't really matter where. What does matter, though, is that one side of the tilt switch goes to pin 7. There's nothing special about pin 7. It's just one of the digital pins. And the other side of the switch goes to ground. Now, it's important to note that what that means is that a vertical or upright pin or a vertical or upright tilt switch is going to ground pin 7 because pin 7 is going to have a direct path through a connected switch to the ground. And if the switch tilts, then pin 7 will be floating. It won't be connected to the ground at all. On older boards, a floating digital input would randomly read as high or low because the computer wouldn't really know what to do with it. And so you'd have to build some kind of circuit outside on the breadboard that would pull the pin up or down depending on what you want to do with it. In this case, Arduinos have a built-in pull-up option for their digital inputs. And so that means you can, in the code, declare that pin 7 is going to be an input and that it's going to be a pull-up input. Pull-up in this case means that when the pin is disconnected, and that's that ambiguous situation where the computer doesn't know what to do, that means that the Arduino is going to read that pin as high. And if the pin is grounded and has a direct path to ground, that would mean that the pin will read low. In our case, if we want to make a tilt alarm, what we would do is somewhere in the code say if that pin reads high, meaning it's tilted, then go do all that stuff with pin 13 that we were already doing, make the lights and alarm go off. In the actual code, it would look like this. What I did was I went to the blink sketch, I went to save as and saved it as blink 2 so that I could mess with it. And you should do the same. And I added 2 lines of code. First one was this underlined bit right here, where I just said pin mode for pin 7 is going to be an input pull-up. And I just explained what that was. Then, in the void loop, I just took exactly the code that was there and I wrapped it with an if statement. So the very first line is if pin 7 reads high, then do all this other stuff. The syntax is pretty simple, just the word if, an open regular parentheses. Digital read and write are easy to remember, just a capital R for digital read. Then in parentheses, which pin do you want to read? And a regular comparison, meaning 2 equal signs. If digital read on 7 means high, then would be the curly open brackets. Do all this stuff that we had done before, and then close that if statement with the curly brackets at the very end. If you get some kind of error, it might be because you forgot a semicolon or something. This is C++, so it gets a little bit picky about syntax. It's not that picky about indentation like Python, but still you have to be careful of some things. Either way, it's 2 lines of code that definitely change the functionality of the circuit. So let's see how that looks on the actual board. I'm going to build it now and show you what it looks like. Okay, so here's my breadboard. I'm going to take one lead of the tilt switch and put it over in, I think it was 40 on the diagram, I kind of forgot. So I'll go with 40 and 45. So off in the middle of nowhere right now. One side, I'll say column 40, is going to go to pin 7. And to complete the circuit to ground, I'm going to bring column 45 over to the ground rail. So that's the whole circuit. And since I've just uploaded that sketch that I showed you, I'm going to now connect the circuit. And if I'm very still, like very still, then when the tilt switch is upright, nothing will happen. But if I move at all, it's got an alarm. And you'll notice when you do this thing that it doesn't take a whole lot of tilt. All you'd have to do is kind of move your fingers around just a little bit, and it'll start telling you that you're moving. So this actually works pretty well as a motion sensor. Just a little bit of tremor or something would do it. So anyways, I'm going to unplug that. And there you have it. You've made a movement alarm. There are a couple of awkward things about the way we did that, though. One of the major drawbacks of the code that we just looked at was that the entire void loop is being paced by the timing of the blinking light. So in order to make the light blink, we're basically telling the entire Arduino, go to sleep for 100 milliseconds, and then do something else, and go to sleep for another 200 milliseconds. And then you can start the void loop over again and read the state of the switch. It doesn't really make a whole lot of sense to be reading a switch only once every 300 milliseconds or so as the pin 13 is making a beeping sound happen. It would be better if you could just somehow keep track of time. And once a certain amount of time has passed, tell pin 13, okay, beep. And in the meantime, every millisecond, you could be checking the state of some other input pins or reading from some other analog inputs even. And we'll get into how to do that next week when we cover sensors. But it's really important to just note that this idea of delaying in order to make a blinking light is something that is good to get started. It makes something active happen in the circuit, but it's not programming logic that you want to follow into the future. It's something we're going to modify immediately with a better way to do this. So a couple final thoughts for our synchronous session. Be sure that you're comfortable with and have built the circuits demonstrated here so far. There's only been a few, but you can see there are some variations, and if something goes wrong, it might take some troubleshooting. It can be a little bit hard to see what the row numbers are, so if something's offset by 1, it can not work and take a minute to figure out, oh, I was in the wrong column, that kind of thing. And if you have time, of course, try out the other projects in the tutorial or online. There's many, many good and well-explained tutorials in this kit, in the materials that I've sent out to you, as well as just by Google searching or going to the Arduino page. There's a lot of YouTube videos. Most of them are meant for hobbyists, so they don't assume anything about your previous experience or previous training. They're really meant for everybody. This is really a general public kind of technology now. So with that, happy hacking, and I'll see you on Thursday.